K nearest neighbors. Let's first understand the term neighbors here. Neighbors refers to the closeness or proximity amongst samples of data. This determines their neighborhood. There are several ways to calculate the proximity or distance between data points depending on the problem to be solved. Most familiar and popular is the straight line distance, that is, the Euclidean distance. Generally, neighbors share similar characteristics and behavior, which is why they can be treated as they belong to the same group. This is the main idea of the simple supervised learning classification algorithm. Now, for the K in KNN algorithm, that is, we consider K nearest neighbors of the unknown data we want to classify and assign it to the group, appearing majorly in those K neighbors. We want to select a value K that is reasonable and not something too big, as it will predict the class having majority among all data samples, or something too small. So hence we need to make sure the value of K is not something too big, nor is it something too small. Let us now see how K nearest neighbors can be applied to text classification. Just as before, we upload the necessary libraries and packages, and we load the data into the collab, right? Collab. We then apply cross-validation for hyperparameter tuning. Here we have 8 parameters currently in use. Algorithm, which is set to auto, leaf size, which is 30, metric, which is Minkowski, symmetric parameters, which are none, and so on. We have 8 parameters for tuning, and but we will tune only one of the following of the 8 parameters, that is k. As we are referring to this as k nearest neighbors, we will tune the parameter k. K stands for the number of neighbors that is needed to be used for default number of queries. In this case, since there is only one hyperparameter, we will perform an exhaustive search directly. We will perform grid search cross-validation. To perform this, we need to define the grid. The parameter grid will be the n neighbors, and we will create a base model for the k neighbor classifier, fitting the three folds for each of the 100 candidates. Totaling, we will be totaling 300 fits. Notice how we were fitting it for 50 candidates in the earlier two models, but in this model we will be fitting it for 100 candidates. And when and because we will be directly and because we'll be directly performing the exhaustive search, we will not work on the three folds and 50 candidates, but we will directly work on the best possible accuracy, which can be obtained when the candidate value is 100. And the best parameter for this can be the n neighbors whose value should be held at 6. So having 6 neighbors, the best possible result can be obtained, that is 94.77%. Since the grid has a space of 5 between each element, we will now cover all the possible n neighbors nearest to 6. Getting the threefolds for each of the 11 candidates, totally 33 fits are possible. And from this, the best hyperparameter was found to be for n grids, which is 6, which is similar to the previous data, and the accuracy remains the same, that is 94.77. We now know the best KNN model. Let's fit it and see how it performs. The conditional probabilities can be obtained using the command KNNC, referring to K nearest neighbors classifier predictor, which chooses the best KNN probability for the test samples. For performance analysis, we will use the confusion matrix, the classification report, and the accuracy on both training and test data. On the training data, the accuracy is found to be 95.98%, and on the test data, the accuracy is found to be 92.81%. We then generate the classification report, in which out of 5 trials, the average precision is found to be 93%. The average recall is found to be 93%. The average F1 score is also found to be 93%. This is similar values to the random forest classifier we found earlier, which was 93%. The confusion matrix is also very similar to that of the random forest classifier.